So far with limits, we've worked with determining them from tables and from graphs. But there is a third way we can determine limits, and that is algebraically, just by using the function itself. So today we're going to look at topics 1.6 and 1.7, which is on determining limits using algebraic manipulation, and then also selecting a procedure for determining a limit. So before we can get into finding limits using algebra, we need to know a few very basic limit properties. So the first one here says the limit as x approaches c of b is b. So if we put numbers with that, if we say something like the limit as x approaches 2 of 6, where it's just a number. Well, in that case, it doesn't really matter what x is approaching. There's no x in the function. It's just 6. 6 is 6 no matter what. So this limit is 6. So this property is really just saying the limit of a constant is that constant. And then properties 2 and 3 are what are called direct substitution properties. So that basically means as long as the function is continuous, if I'm doing the limit as x approaches c of x, well, that is just c. I can just plug that number in for x. And then it's the same thing if there's a power. The limit as x approaches c of x to the n, well, I can still just plug in c for x and get c to the n. So those are called direct substitution properties. I can just plug the number that x is approaching in for x. So examples 1, 2, 3, and 4 are pretty simple here. Example 1 just says the limit as x approaches 3 of 5. Well, 5 is just a constant. The limit of a constant is that constant. So this would equal 5. On example 2, we're finding the limit as x approaches 2 of 4x squared plus 3. Now, we could use a lot of limit properties here. So I could use the scalar multiple property and the sum property to rewrite this as 4 times the limit as x approaches 2 of x squared plus the limit as x approaches 2 of 3. And then here I could use this power property to say this is really equal to 4 times 2 squared plus, well, the limit of the constant here is just 3. So 4 times 4 plus 3, this would be 19. So I could use 3 different limit properties here. So I could use the scalar multiple property to pull the 4 out front. Use the sum property to split this apart into 2 different limits. I could use this constant property to say that limit is just the constant itself, and this direct substitution property to just plug in the 2. But we really don't need to be that technical with it. We can just do a direct substitution. We don't really need to split it apart into all those different pieces. I could just say this is equal to 4 times 2 squared plus 3. I can just plug 2 directly in for x. All it is a direct substitution. So this limit would equal 19. So anytime you have just a polynomial function where there's no denominators, no square roots or anything, you can just plug in the number that x is approaching for x, and that will let you find the limit. Example 3, there's a little bit more to be cautious about. It's the limit as x approaches 1, and notice there is a denominator. So anytime there is a denominator, we have to make sure we're not letting that denominator equal 0. So maybe we'll be able to still do a direct substitution here, maybe not. Let's take a look and see. What happens if we plug in 1? Well, then this would equal 1 squared plus 1 plus 4 over 1 plus 1. So in this case, it would not make the denominator 0. So because this is not making the denominator equal 0, yeah, we're good to just do direct substitution. This would be equal to 6 over 2, which is 3. So this limit would equal 3. So even when it's not just a polynomial function, as long as we're not creating something where the denominator equals 0 or like the square root of a negative number, we're still good to just do a direct substitution. And then example 4, we have a trig limit here, so we'll have to use some unit circle stuff. The limit as x approaches pi over 2 of sine of x. Well, we can still just do a direct substitution. I can still just plug this in. This would equal sine of pi over 2. Now, sine of pi over 2 is something that we will be expected to know on the AP test, or at least be able to figure out. So, just looking at that, think of your unit circle. Remember, 1 full revolution around the circle is 2 pi radians. So halfway around the circle would be just pi radians. So pi is over here. Halfway to that would be pi over 2, which is what we want. Pi over 2 is up here at 90 degrees. So we're talking about this point right here. Remember, sine is the y coordinate. So this would be equal to 1, would be the y coordinate up there. So sine of pi over 2 is 1. And these trig values at least 0, 90, 180, 270, and 360 degrees. We'll need to know at least sines and cosines of those, and probably some tangents as well. So make sure you're not forgetting about unit circle stuff from last year. So those direct substitution problems are really easy. Just plug in the number and evaluate. However, not all limits can be taken by direct substitution. There are some issues where if you plug the number in, you might get 0 in the denominator. So we need to have strategies for how to deal with something like that. So examples 5 and 6 are what are called factor and cancel problems, and you'll see why we're calling them that in just a minute. But in example 5, it's asking us to find the limit as x approaches negative 3 of x squared plus x minus 6 over x plus 3. So if we try just plugging in negative 3, that would be negative 3 squared plus negative 3 minus 6 over negative 3 plus 3. Well, right away I see a problem with the denominator. Negative 3 plus 3 is 0, but we also have a problem with the numerator too, because negative 3 squared is 9, negative 3 and negative 6 would be minus 9. We get 0 over 0, and that's a problem, because this doesn't exist. So the function is not defined at x equals negative 3. But that doesn't mean the limit doesn't exist. It might be a situation where there's a hole in the graph. So it might mean at negative 3 there's a hole, but the limit could still exist, because we could still be approaching the same thing from both sides. So in this case, what we need to do is try to simplify or change the function a little bit. And we're going to do that by factoring and canceling. So we're going to just manipulate the function a little bit. We're going to try factoring it and see what happens there. So this function right here would be equal to, we still have to write this limit as x approaches negative 3, because we're still doing the limit. And then we're just going to write it in factored form. So we're going to factor the numerator. So x squared would be x times x. I need factors of negative 6 that add up to 1. So that's positive 3, negative 2. And we're still over x plus 3. So we factored it. We now have a common factor that we can divide out. This is still equal to, you cannot forget this limit expression here. We need to make sure we're still writing that. The limit as x approaches negative 3 of just x minus 2. Now that we have simplified the function, we are able to do direct substitution. Now we can plug in negative 3. So this would be equal to negative 3 minus 2, negative 5. So this limit is equal to negative 5. Notice at each step, I had to keep writing limit as x approaches negative 3. I can only stop writing that when I actually plug in negative 3. Until you actually do the direct substitution, you need to have limit as x approaches negative 3 written every step of the way. If we forget that, then what we're saying is this limit, which is equal to negative 5, that we just figured out, is equal to x minus 2, for example, if we forgot that limit statement here. Well, that's not necessarily true. Negative 5 is not equal to x minus 2, because 1's a number, 1 is an expression. So just make sure when you are simplifying these functions, every step of the way, you are writing that limit as x approaches whatever x is approaching. You can only stop writing that once you've actually plugged the number in. Let's look at just one more for today. Example 6, find the limit as x approaches 1 of x cubed minus 1 over x minus 1. So again, if we try a direct substitution here, we're going to end up with 0 over 0, because it would be 1 minus 1 over 1 minus 1. So that's our indication. We need to do something. So maybe we notice, maybe not. This numerator is a special type of binomial. It is a difference of cubes. Because x cubed is a perfect cube, 1 is 1 cubed. So that's a perfect cube as well. So we're again going to be able to factor. Now, remembering how to factor a difference of cubes is a little tough, so we'll walk through it here together. But this is going to be equal to, remember we're still writing limit as x approaches 1 of, there's nothing to factor in the denominator, so I'll leave that. Remember, a difference of cubes always factors as a binomial times a trinomial. The binomial is just going to have the 2 cube roots. So the cube root of x cubed is x. The cube root of 1 is 1. I'll worry about the sign at the end. So the binomial is just the 2 cube roots. The trinomial is the first cube root squared, then the product of the 2 cube roots, so x times 1, x, and then the second cube root squared. So 1 squared is still 1. So the binomial is the 2 cube roots. The trinomial is the first one squared, the product of the 2, and then the second one squared. And then for the signs, I always remember the acronym SOAP. So the first sign is the same as the original problem, so a minus. The second sign is the opposite of the original problem, so that's going to be a plus. And the third one is always plus, so plus. So x minus 1 times x squared plus x plus 1. Now that I've factored it, we can see a factor will cancel. X minus 1 over x minus 1 will divide out. So this is equal to the limit as x approaches 1 of x squared plus x plus 1. And now we can do a direct substitution. We can plug in 1, so 1 squared plus 1 plus 1. This limit would equal 3. So we'll stop there for today. There's a few more examples on the back of some different strategies, but our primary strategies are going to be direct substitution. Plug it in, see if it works. If it does, awesome, we're done. If it doesn't, we maybe need a different strategy. Our first alternate strategy is going to be factor and cancel. There's some more strategies on the back that we'll get into tomorrow. So let me know if you have any questions, and I'll see you tomorrow.